Swayam Prabha. Digital India. Educated India.
This is the fourth slot that I am getting into, because I have not been able to complete whatever I wish to do within the 2 slots given to me. So, I thank Professor Anbarasan for giving me this extra slot. So, tell me one reaction, either chemical reaction or physical transformation of interest to you. Tell me any one. Tell me any one reaction or physical transformation of interest to you. Any one. Has to be a little quick. Huh? Rusting, again, rusting is the one that, okay, I have no problem writing rusting. Huh? Chemical reaction, can you think? Any reaction you can tell me. Anything else? Cis-trans isomerism, shall I write cis-trans isomerism? Is that okay? Organic, never touched any organic reaction. Is that okay? Okay. So, we will touch this, okay. So, this is a gas. This is also a gas. So, this is a cis isomer. This is a trans isomer, and number of carbon atoms is 4. So, it is butene, isn't it? Cis butene, trans butene. Just imagine this is in a big flask, okay. So, we are going to apply this. The flask essentially has to have some opening. So, it is a closed system. So, we are going to put a flask, with a cork here. So, this is the reaction of interest, isomerization of cis butene to trans butene. Now, what is the whole purpose of this lecture? The purpose of this lecture is under normal conditions of temperature and pressure. Normal conditions of temperature and pressure are pressure equal to 1 atmosphere, temperature 273.15. It's never 25 degrees, only in some places, not in Chennai certainly, okay. The question that you are interested as a chemist is, will this transformation take place? Spontaneously. Spontaneously means what? Spontaneously means what? Without any external intervention. Very good. Don't tell without any external intervention in a flask will this take place. That is the first interest for you. Okay. Cis butene, will it become trans butene? If so, what is a real interest of an organic chemist? What can be the yield? What will be the quantity of trans butene formed? What will be the quantity of cis butene? And then whether they can be separated. Whether the cis and trans can be separated. Trans may be useful for you in some application. Cis may be useful for you in some application. So, what you are interested is in finding out the equilibrium constant K P, which is given by concentration or partial pressure of trans butene divided by cis butene, right. Okay, here you can also write, instead of concentration, you can write partial pressure of trans divided by partial pressure of cis. If you know this number, let us say it is 2.3, just for argument, at 298 Kelvin and 1 atmosphere pressure, let us say it is 2.3, some number, okay. Is that enough? You are happy with that number and you are happy with separation? Just the number is enough? Okay, predominantly it will be trans, cis. You are also interested in the mechanism, pathway, but that is not in thermodynamics, that is not the concern of thermodynamics. Thermodynamics is more concerned about whether it will happen. What more can interest you about this? Can you manipulate the yield? Can you make it more trans or can you make it more cis? Then for that you have to understand the equations that govern this equilibrium. So, that is what today's lecture is all about, delta G, which will tell you something about spontaneity of natural transformations. Next thing is, how is it affected by parameters or variables of the reactions such as temperature and pressure. That is the purpose or goal of today's lecture, and I will try to give you some really practical examples, okay, and with that we will conclude the lecture, okay. So, we already saw this, I will quickly, you know this, entropy change in the universe is not a good criteria because natural transformations do not occur under conditions of constant internal energy and volume. Though natural transformations do not occur under these conditions, they occur at normal temperature and pressure, preferably in a closed system like this, okay. So, you need to look at the new property which we saw in the last class, that is what I am trying to drive you. Last class, this is where we left, okay. We started from this second law criteria, that delta S system plus delta S surrounding should be greater than delta S universe, equal to delta S universe should be greater than 0, and that is a second law condition for spontaneity. We did not prove it, we simply took Clausius inequality and we simply said this is the condition. Now, the definition is that delta S surrounding is given as heat change in the system divided by T. This is a very important parameter you must remember from examination point of view, okay. Entropy change in the surrounding is given as heat change in the system, whatever heat change that takes place in the system with a minus sign. If it is an exothermic reaction, you will put a plus sign. If it is an endothermic reaction, you will put a minus sign to the heat, divided by the temperature at which the surrounding will accept the heat. It is not the temperature of the system. Surrounding has to accept heat. Entropy is always heat change by temperature at which heat change takes place. So, this is very important definition. You put it here. So, delta S system equal to minus of this plus this becomes minus delta H system by T. It is still the second law. Now, multiply by T, you see that this is nothing but T delta S system minus delta H system is greater than 0, and that is a condition for spontaneity. And since there is a minus sign here, I just rearrange it, multiply this by minus, that means this will become plus delta H system minus T delta S system. See, everything is system. I have written SYS means property of the system. Less than 0 is the second law. Then we had a special term S delta T, it does not matter because T is constant. S delta T you add, P delta T you add, V delta T you add, that does not matter, delta is 0. So, if you add that, you get a new property, delta H system minus delta of Ts is less than 0 is the criteria for spontaneity, and we define this property, or Gibbs defined this property as free energy. Free energy, delta free energy, which is Gibbs free energy, must be less than 0 for a spontaneous transformation. This condition immediately you see is the condition for a transformation to take place in a system, that is constant temperature and pressure, and it is a property of the system. Why do you want the property of the system? If you want to do a reaction in a bottle, then I can measure the properties. Okay, if I do the reaction in a chemistry department, it is very difficult to measure because so many things are happening all around us. So, you need to measure the property of the system. Measurable property, condition should be normal, like normal temperature and pressure, and if you find something and that is negative, spontaneous. And once you do that, you have to find out how can we study the other properties, like how does it vary with temperature and pressure. So, that is where this is the example you can give. Anything you can write here, ammonia synthesis, anything you can write, okay, anything you wish to write here. Reaction of interest. So, this part that we are studying is something that enables you to, if you want to manipulate, if you want to change the outcome of a reaction, it enables you to change the outcome. After all, we are interested in the outcome. What is the point in sitting in this class if 1 year from now you are not best placed in the best PhD program, assuming that you are going to be interested in the PhD program. That is the outcome, desired outcome, right? In addition to attending these classes, seeing the lecture notes, doing problems, being in touch with the faculty who are teaching you, these are all the parameters you should play with, so that 1 year from now you are where you want it, right? That is the outcome. After all, everybody is interested in the outcome of a transformation. So, in addition to Gibbs free energy, there is one more free energy which uses the internal energy of the system. A equal to U minus Ts is known as Helmholtz free energy, and G equal to H minus Ts is known as the Gibbs free energy. What is the meaning of this Gibbs free energy and Helmholtz free energy? What is the physical meaning? Okay. Now look at Gibbs free energy. H is an enthalpy term. Enthalpy term you already know is heat absorbed or given out at constant pressure, right? Already you know from first law. So, the meaning of this Gibbs free energy is total heat transformation minus that which is not available to do work. Okay, this amount of heat Ts gets dispersed away. Like State Bank of India, I ask you to deposit 100 rupees. This is 100 rupees, and this is what you are going to. You are the person who are going to do the work, and whatever work you take away, balance you put, that alone will be available in my account for spending. Okay, so total energy available in a transformation due to chemical bonds minus energy that is not available to do work. That is a definition of Gibbs free energy. In many devices there is no gases, everything is liquid and solid. So, for solid state devices, constant volume is a standard condition, right? For example, a diode, a semiconductor, etc. For them, generally Helmholtz free energy is the preferred criteria because there is no volume change. Okay, generally in chemistry we use G only because we use gases. Largely volume change occurs in chemical transformation. That's why G is used in chemistry. This is used in physics largely. Okay, with that we will go straight to now dG equal to dH minus T ds minus S dt. That comes from differentiating G equal to H minus Ts, and dG change at constant T and P, which is the condition for spontaneity, normal temperature, normal pressure. You see that dH at constant pressure will be nothing but heat absorbed or given out minus T ds system. So, this is the condition for spontaneity. Since dQp is always less than T ds, remember the second law, heat absorbed will always be less than this. So, for a spontaneous transformation of system, dGTP should be always negative. That is a condition for spontaneity. Okay. Similarly, you can do the exercise for Helmholtz free energy under constant volume and temperature. If dA, the change in Helmholtz free energy, if it is less than 0, that is a condition for spontaneity. So, we have touched spontaneity. Okay, there is some property of the system. In this case, chemistry says it is the Gibbs free energy. The Gibbs free energy change should be negative. Can we measure Gibbs free energy? Of course, you can measure. Using properties of the system, you can measure. Conditions are very simple. Temperature, pressure are normal. Okay. So, that is why this becomes very, very important topic in chemistry. And to get here, I had to go through the previous 3 lectures. This is where you have to start normally in after BSc. But it's very BSc, sometimes these are not covered so nicely. So, that is why this took all along 3 full lectures or 3 rather 3 into 2 6 lectures to get here. Okay. So, these are the conditions for spontaneity. Now, did you get the lecture notes I sent to one of you? Okay. Now, let us see. A very important problem is whether carbon diamond to carbon graphite. Okay. What will be the heat of formation of this reaction? Graphite is the more stable form, diamond is the less stable form. So, suppose you want to find out whether diamond will become graphite, you go look at the combustion data of diamond, which can be done by thermocalorimetric measurements. You can find this out, and graphite you can find this out. Subtract delta G for this transformation is minus 3 kilojoules. Therefore, diamond will spontaneously transform to graphite. Okay. So, diamond whatever one is wearing, diamond ring, everything, someday will become graphite. Which will be the day? Because it is going to become spontaneous, can you say which day it will become black? It can take 1 billion years, it can take trillion years, it can take billion trillion years, we do not know, because chemical kinetics has nothing to do with chemical thermodynamics. Chemical thermodynamics will say, like Buddha said, all people born out of woman must die someday. Okay. Anything else, when will they die? That I can't tell. Somebody say go to astrology, somebody said go to this and that. Okay. So, this is all it will tell you is the obvious, whether it will obvious will happen or not. Beyond that, without disturbance, that is where. So, diamond will become graphite. Then we will analyze this a little later as another problem. So, what the next problem is green production of hydrogen gas. Now, I told you at the beginning I will discuss this, remember. So, green production of hydrogen gas means hydrogen gas is produced from water by electrolysis. The electrical energy must come from wind energy or solar energy, then it is called green hydrogen. Okay. So, if you want to calculate what is the standard Gibbs free energy associated with the formation of hydrogen gas from water using green energy, then what you need to do is look at the whole reaction. So, you go to Atkins page 993 to 1000, 8th edition, you will find the following data. Standard heat of formation of liquid water is this, standard entropy of liquid water is this, standard entropy of hydrogen gas is this, standard entropy of oxygen gas is this. Why do you want this? Because you need a balanced chemical equation. I told you always start from a balanced chemical equation. H2O liquid upon electrolysis will give hydrogen gas and half oxygen gas. Conversely, hydrogen gas plus half oxygen gas with a catalyst will give you H2O liquid. This reaction is spontaneous as written. This reaction is non-spontaneous. Why it is non-spontaneous? Because the free energy change associated with the reaction H2 plus half O2 or the reverse reaction is given by this equation delta H minus T delta S, and delta S can be calculated from the entropy data given. All the entropy data are given. From the entropy data you calculate the product minus reactant, and the whole overall entropy change in the reaction is 163.34 joule per mole per Kelvin. The free energy of formation of liquid water is given by delta H minus T delta S. This data is given. You go back, you see that this data is given. This data is already given here. So, substitute delta H minus T delta S, overall value is minus 237120 joule per mole per Kelvin. The standard free energy associated with the formation of liquid water, formation of water is a huge number. It does not matter huge number if you write this billion, trillion or minus 2 or minus 0.2, write minus 0.002, all it matters is it should be negative. Does not talk about how fast it will take place. It will not talk about the quantity of material formed. It just simply tells you about the direction. It can be any number as long as it is not 0 and less than 0, it is spontaneous. So, the standard free energy of formation of liquid water is this. You can calculate the standard internal energy change by using this formula U, delta U and H are related, H equal to U plus PV, delta U equal to delta H minus P delta V minus V delta P, constant pressure, so only P delta V term will survive. How do you calculate P delta V? P delta V for a perfect gas is nothing but delta N RT, because PV equal to nRT. Okay. So, delta N RT can be substituted by taking the balanced chemical equation. The balanced chemical equation tells you delta N is minus 1.5 moles or 33.6 liters. So, P delta V is given by this number multiplied by 101.325 to convert liter atmosphere to joule. So, this is the PV work associated term, and internal energy change is minus 289,204.5. So, like this for every reaction you can find out every tiny balance sheet, like I told you about accounting, where is this amount of money going, where is this amount of money going, or in the case of an auto I told you fraction of heat loss to the tires, fraction of heat loss to friction between metal bodies, fraction of heat actually lost as heat, right. We did one problem, remember, for 1 kilogram of methane gas, 55,500 kilojoule of energy, and actual energy or work done is only 36 something. Balance has to be accounted for in terms of breakage, where exactly it is taking place. Like that we can do this in this example, calculate delta U, you can calculate delta H, delta S, delta G, etc., etc., etc. For every reaction you can do that. Okay. So, the free energy of formation of liquid water is minus 237,120 we saw. So, how much of electrical energy you have to put in order to electrolyze water is delta G equal to minus NFE. Okay. If this is the amount of energy required for formation, breaking will be minus of this. Okay. So, you calculate N, number of electrons involved, 96,500 is Faraday constant, E naught 1.23 volts. So, theoretically speaking, if you take water, add a drop of sulfuric acid to make it a little bit conducting, or add a salt to make it conducting. Water is not a conducting material. Apply electricity across the electrodes, anode and cathode, minimum amount of volt you have to push in is 1.23 volt. Anything less than 1.23 volt, it will not happen spontaneously in the reverse direction. That is, electrolysis of water will not take place, minimum. But in reality, it will be more than the minimum because of there are number of other effects. Okay, you will learn that these are all kinetic effects. In practice, there is over potential, charge gathering, and so many other factors take place. But minimum amount thermodynamics tells you is 1.23 volt. Without 1.23 volt, water will not electrolyze. Okay, so when water has to be electrolyzed, you need this much minimum. And when you do green production of hydrogen gas, tomorrow you end up in a factory. We need, I told you in India, we need green hydrogen gas because of the railway engines, like expected anytime within a month or two, you will get Sonpet or something. I said Sonipet, I told you the example, 90 kilometers. Okay, it is going to be run with green hydrogen gas. And the green hydrogen gas is going to be used in a fuel cell, where platinum is going to be the catalyst that will convert hydrogen to water and generate this minimum 1.23 volts, okay, minimum, and that will be used to push the engine to do work. Okay, so you will have to do all this calculation, energy cost associated with the setting up of wind energy or solar energy. There is a cost associated with it. Nothing is free, no. So to get green hydrogen, you have to have a wind energy plant or a solar energy plant, which is going to cost land, people to maintain equipment, everything, right? And then there will be cost of building up the hydrogen fuel cell. That doesn't come free. You have to set it up. That will be the cost. Okay. And in return, what will you get? Actual energy produced from 1 kilogram of hydrogen, green hydrogen, using an internal combustion engine. Internal combustion engine will convert it at 50% efficiency. Okay, again, heavy loss. Okay. So remember, when you have to really do the total actual energy converted to useful work, you will find that, see, there is a lot of talk about green hydrogen, grey hydrogen, this is the way to go forward, etc., etc. All that is okay if natural abundance of hydrogen is there. If you have hydrogen available in plenty in this grounds, in this earth somewhere under the earth, somewhere where it can continuously produce free hydrogen, and all this makes sense. But when you have to produce hydrogen, what is the minimum work you have to do? 1.23 volt you have to give. Where will you get that 1.23 volt? You have to generate power. And after getting that hydrogen, you convert it to water, only half is available to do work. Okay. Does it make any sense? But oftentimes we have no choice. When you go and tell people, this is not the best way to generate green energy, this is not the way to do, nobody will listen to you, because this is an international standard that has been set. And all that thermodynamics tells to help you is to grasp the fundamentals. Why are they being so not so smart in trying to generate power from hydrogen when hydrogen is not available? The reason why fossil fuels are still important is because they are available without you doing any work. You don't have to set up anything, all you need to do is dig, and you either get methane gas, ethane gas, or you get which you have to crack to get oil. But the thing is, energy is free. No Gibbs free energy, God free energy. Okay, G here is God free energy, or no, if you don't believe in God, no God free energy. Okay, whatever be the case, this energy is available for you free. Whereas green hydrogen is not something, from the thermodynamic point of view, it simply doesn't make any sense. If I want to come from ground floor to the second floor, if I have to do 3 times, right, in the lift, suppose there is some complicated mechanism by which you come, right, very complicated mechanism, lift goes like this, on the ground floor itself, goes like this, goes to the first floor, does 1 full round, comes to the second floor, doesn't come to the place where you will actually want to go, does 2 rounds and then comes here, you would prefer to use a staircase, right, because it's going to take much more time and test your patience. So these sort of things are very nice to say that this is the way to go forward. This is not exactly the way to go forward from the thermodynamic point of view. You are unnecessarily spending energy, more energy to get 1 joule of energy. For 1 joule of energy, you are going to spend 2.5 joules. Okay, so that is the important thing. So you should keep this figure in your mind. It will help you to understand. So for comparison, you see the Gibbs free energy accompanying the combustion of methane gas You can do this again, Atkins, page 993 to 1000, all the data is available. Write the chemical equation of importance. This is the chemical equation of importance. This is combustion. Calculate delta G of reaction. You need delta H for that, delta S for that. S data is given in Atkins, H data is also given in Atkins. You pump everything. So what you will get will be per mole of CH4. Per mole of CH4 is 16 grams. 16 grams of CH4 or methane gas will give you 818 kilojoules. 1 kilo will give you accordingly 1000 by 16 into this number. Huge amount of energy is available in methane gas. Why are you trying to make hydrogen gas? Only God knows. Okay, what is the intention or purpose of doing all this thing? Sometimes people say it is to develop the science. The science is developed so that some methodology of making hydrogen, alternate method is available. I don't understand this at all. Okay, you don't reduce carbon dioxide to carbon. Nature takes care of it. You convert carbon to carbon dioxide and keep quiet because that is free. Carbon dioxide to methane gas is not free. You have to pump more energy than what nature did in bringing it from carbon to carbon dioxide, and that is foolish. Okay, but then many times human beings are not exactly rational. They do all sorts of things, and again I tell you the purpose is to understand that this transformation in comparison to the previous transformation gives you lot of energy without you doing anything. All you need to do is bring air, light it up, kaboom, kaboom, that's all. Gives you lots of energy. Some goes away as heat, some is useful to make useful work. Okay, so with that, now this is what happens in our body. These are all examples. Again, page 98 of Atkins. Glucose is converted to carbon dioxide in our body. You can do this exercise either from Atkins or from my notes. You can find out this total energy. You will find that a lot of energy is available from a mole of glucose. But 1 mole of glucose cannot be consumed directly. You have to consume in very, very tiny amount because cell will burst if so much of energy is available for it. Okay, this I told you also. So you can actually calculate that natural things like methane combustion, glucose combustion gives you enormous amount of energy. All you need to be a little more patient. Wait for nature to do the turnover on its own. Nature will turn over carbon dioxide to methane someday. It will turn over carbon dioxide to glucose someday. If you live in dynamic equilibrium with nature, nature will take care of your needs. But you are in great hurry and you take a hammer and hit nature, okay? As much as fools only will do this, and which we are all doing. We means all throughout the world, especially the developed world. It takes a hammer and hits nature so hard that nature cannot really respond. Okay, and that is not a smart way to do. That's not really a smart way according to thermodynamics. Thermodynamics tells you, oh, hey fool, don't do this. Okay, wait, be patient. That is the lesson you learn from chemical thermodynamics, that some things are better left for nature to do a better job. It takes care of the details. You don't have to worry. Now, with that, delta G as a criteria for spontaneity is done. We'll go to Maxwell equations. Okay, there are 4 Maxwell equations, and I'm going to give you with one example what is the usefulness of Maxwell equation. There are a number of examples. I'll give you only one example. Okay, and this Maxwell equations, there are 4 of them. The first one we start from this equation. Okay, this equation is familiar. d equal to T ds minus P dV. Okay, this is the nothing but the second law and first law put together. Okay, so this is known as a thermodynamic equation of state. One thermodynamic equation of state is du equal to T ds minus P dV. So what it implies is u is a function of S and V. Otherwise, it will not be du equal to T ds minus P dV, right? So if u is a function of S and V, in maths we can write du is dou u by dou s at constant V ds plus dou u by dou v at constant s dv. We can write this, that expansion is allowed. Okay, then you compare this with this. You will find that temperature is nothing but variation of internal energy with entropy at constant volume, and pressure is nothing but variation of internal energy with volume at constant entropy with a minus sign. Okay, this is one way of looking at pressure and temperature. We normally cannot look at pressure and temperature in this manner, very complicated. Why would anybody look at temperature in this manner? When you touch and feel, when you have a thermometer to tell you it is more or less, why would you use an equation like this? But there is some usefulness to looking at it this way, and you are going to see why it is so. Okay, because we just said this. You remember f of x, f of xy. If f is a function of x and y, given by df equal to g dx plus h dy, you know that if dou g by dou y at constant x equal to dou h by dou x at constant y, this is also known as Euler reciprocity relation, then f is a perfect or complete differential. We said this earlier when it came to q is not an exact differential, q by t is an exact differential. Remember that, okay? Since u is a state function and it is exact, we know that. So, dou u equal to t ds minus p dv, immediately what you can do? Take dou t, take this t, dou t with divided by dou v equal to dou p divided by dou s. So, this is a form of Maxwell relationship. Maxwell relationship is nothing but Euler reciprocity relationship applied to every thermodynamic equation of state. There are 4 thermodynamic equations of state, one you just saw. So, for that one thermodynamic equation of state, you apply Euler reciprocity relationship and what you get is Maxwell equation. Okay. So, 1 du equal to t ds minus p dv, you get this relationship. This is known as Maxwell relationship 1. Okay. Now, do that to second one. Let us start with this same equation. You know that dh equal to du plus p dv plus v dp because h equal to u plus pv. Okay. So, dh equal to du plus. Now, you put this in this equation, you will get dh minus v dp equal to t ds. This is a second thermodynamic equation of state. It is an equation of state where h is involved. Previous one involved u. Now, it involves h. Okay. Very simple. From this, automatically you can come or arrive at a Maxwell relationship as dt, differentiation of t with respect to dp, dt by dp, dou v by dou s, dou v by dou s, and that is the next second Maxwell relationship, which is nothing but Euler reciprocity relationship. I am going to send the notes to you. Don't be in a hurry. Carefully listen. I will send it to you at the end of the class. Okay. So, like this, you can write 2 more relationship. You can write for dA. Do this exercise. You will get one more thermodynamic equation of state, and for dg you get one more thermodynamic equation of state. Among all the equations of state, the one that is most important is this, dg equal to v dp minus s dt. This is the most important equation. There are 4 thermodynamic equations of state that relate all the state functions u, h, g, a in terms of variables. But among the most important is dg equal to v dp minus s dt. From the chemistry point of view, it is known as Gibbs-Helmholtz equation. Okay. So, dg equal to v dp minus s dt, you apply the Euler reciprocity relationship dg equal to v dp minus s dt. So, what we will do? Dou v, dou t, dou s by dou p, and that is the Maxwell relationship. That is all. Maxwell relationships are nothing but Euler reciprocity relationships applied to the 4 equations of state, out of which one it is enough if you remember one, but at least one you must remember. If you have difficulty, start from the first law, apply the second law, you will get one relationship at least, and from there you can get the other in no time. Okay. Now, with that, let us see application of Maxwell relationship. What is the relevance of Maxwell's relationship? Is it really useful? Okay. So, one of the Maxwell relationship is dou p by dou t at constant v equal to dou s by dou v at constant t. It is one of the relationship. For a perfect gas p v equal to nRT, so dou p by dou t is nothing but RT by v, which is R by v. Okay. Now, R by v equal to the other one, dou s by dou v. So, here we started from this side, applied p equal to RT by v, and this side still remains. So, we get R by v equal to minus dou s by dou v at constant t. So, what is ds? R dv by v, and what does that lead you to? Delta s equal to R ln v2 by v1. Maxwell, Boltzmann proposed this without invoking thermodynamics. Okay. This is actually a very powerful relationship, and sometimes, you know, it's really interesting, or It's important that many a times, people do not come up with theory like from their head. They do not come up with theory just like that. Okay, I'll give you at least Maxwell, Boltzmann came up with this equation on his own. It is still written in his, where he is buried. Okay, there is a small marble stone that says Maxwell, Boltzmann born this year, father, mother, etc. And it says S equal to K ln W, where he is buried. Okay, that is his finding. So these things, how do they normally come? Many a times there is a school teacher when it comes to quantum mechanics. Okay, when it came to quantum mechanics, hydrogen spectrum, etc. It all started with Bunsen burner. Bunsen burner, blue color flame, many things give color, no? So the color spectrum, there was a school teacher who found out that the energy difference, whatever color that comes out, he could correlate it by an equation 1 by n1 squared minus 1 by n2 squared. The color, wavelength of the color, he could easily correlate with 1 by n1 squared minus 1 by n2 squared. He put n1 equal to 1, n2 equal to 2, he gets one color. Balmer series. You passed, you have studied, right? Right? School teacher, physics school teacher, 10th standard, he was teaching 10th standard, and he came up with this relationship 1 by n1 squared minus 1 by n2 squared. A school teacher came up with this relationship. Somebody who is very smart, Bohr was a very smart guy. He said, here is a mathematical equation that describes what is observed in nature, and all I have to do is somehow come up with a theory that will fit in, and that is why Bohr came up with this theory of, in my opinion. Okay, Bohr has not written this explicitly. For me, it simply doesn't make sense when somebody has discovered and observed a relationship. You come up with a theory, don't even mention about this guy. Okay, this must have worked in the back of his mind. Then he comes up with Bohr's theory of atom, consistent, because this eventually you can see in Bohr's theory as well as you can see that in Schrodinger's theory. Okay, whatever you see, the mathematical forms, they exist in nature. Whatever happens in nature, the mathematical forms you can easily derive by or doing experiments, then come up with a theory. Like that, in this case, he randomly or by chance or something, he came up with this, Boltzmann came up with this constant, and that seems to be consistent with the thermodynamic picture. Thermodynamic picture leads you to Boltzmann constant. So Boltzmann constant initially was just a proposal. Now there is a thermodynamic basis for it. Okay. So what will you do if you have to apply this Maxwell relationship for a perfect gas? So let us take a perfect gas. So U is a function of S and V. We do this regular differentiation, and then you use the Maxwell relationship dou P by dou T, the same one that we used earlier. And when you do this for a perfect gas, it is what you already know. But when you do it for a real gas or a perfect gas, what you will get is that this whole factor becomes A n squared by V squared. You do this at home, you will find out that this factor is dou U by dou V is non-zero. It is 0 for a perfect gas, but for a van der Waals gas, it is A n squared by V squared. So the internal energy of a real gas, varies with volume. For a perfect gas, it doesn't vary with volume, because perfect gas have no volume. Perfect gas are particles with nothing. They are particles, but they don't occupy space. Okay, that is the definition of a perfect gas. Real gas actually occupies volume, so that volume varies with V, and A n squared by V squared is a term. For a real gas at constant T, internal energy decreases with increasing V, because real gases occupy volume or space. Okay, so this is something that again Maxwell relationship or Maxwell equation helps you to distinguish between a perfect gas and a real gas. Real gas has really space, something is there, and that is why you get variation of internal energy with volume. Now summary of the second and third law, again and again I keep doing this because it is important. So positive entropy change in the universe is the basic criteria for spontaneity, and the convenient way to do it in a system is to use G. That is all. This is the summary of the lecture so far. Now last part, I have exactly 15 minutes. Okay, try to finish it in 15 minutes by, I'll take a small break to drink water, and G variation with P and T. G as a parameter, how does it vary with pressure and temperature? So I'll switch so that you can have a look at it. The purpose is calculate the free energy change as a function of pressure and temperature. So that's what, and then we solve problems, actual problems. So we will only consider closed systems. I told you chemistry only closed systems. No open system, isolated system doesn't exist. Only closed systems. No work other than PV work, pressure volume work. And already you know this is the fundamental equation of state. Even in sleep you should be able to recall this, dG equal to VdP minus S dt, and then you can actually go back and forth very easily. Anything, one thing you remember, okay, any one equation of state, that is what I am saying. Okay, so dG for 1 mole of a perfect gas is, so what will happen, dG equal to VdP minus S dt at constant temperature, right. So this I will rub, this part I will rub. So one equation of thermodynamic equation of state is VdP minus, and if I do not write, it is all only for the system. Everywhere I do not want to write SYS all the time. So at constant T, dG equal to, so if I want to find the transformation of state from 1 to 2, what will I do? Transformation of state from 1 to 2, isn't it? 1 to 2, so that will be 1 to 2 again. And V, if I put perfect gas, for a perfect gas, V equal to RT by P. So this will become G, it will become delta G, okay, and limits we are yet to define, we will wait, okay. RT ln, so limits 1 to 2, I will keep 1 to 2, I will tell you what 1 to 2 is. 1 to 2 we will define. So 1 will be 1 atmosphere, okay, other will be another, whatever be the change you want to show. So delta G will be G at some pressure P minus G at P equal to 1 atmosphere is equal to RT ln P2 by P1, but P1 is 1 atmosphere, isn't it? So the Gp minus G at 1 atmosphere, what is the symbol for this? Standard pressure. So G at P minus G standard state is given as RT ln P of, at the desired pressure, if you want to find out the free energy, you need to know what is G standard. G minus G standard equal to RT ln P. Really important relationship that takes you to equilibrium. Okay, this is a very important relationship that straight away takes you to equilibrium. I am going to take you one example and show you how Kp we will see for not cis-butene, trans-butene. We will see a case as the manufacturing of ammonia, which is a very important industrial process. N2 gas plus 3H2 gas giving rise to 2 ammonia gas. Ammonia gas is so important to the world. Ammonia, from ammonia you can make ammonium nitrate fertilizer, ammonium nitrate explosive. Iran and Israel need it very badly, okay, they need lot of this today, okay. So also for plants, you know, urea, from this you can make urea, and this chemistry, there is something known as law of mass action. What does the law of mass action say? What does law of mass action says? Q equal to NH3 the whole squared divided by N2 H2 the whole cube, or P NH3 partial pressure of ammonia squared divided by Q is a reaction quotient. At any point in the reaction, this Q will continuously vary until the system reaches equilibrium. Okay. So, here suppose how will I relate this to this equation that we just derived? This part I am going to rub. Okay. So, if for each and every term you write the free energy for each and every term, free energy of nitrogen gas in terms of this equation, free energy of hydrogen in terms of this equation, free energy of ammonia in terms of this equation that we just derived, you will find that this will lead you to delta G equal to delta D double dagger plus RT ln Q, where Q has been defined. Okay. So, this is just a plain simple application of the thermodynamic equation of state to some transformation N2 plus 3H2 giving, all we did was just plugged in for nitrogen this free energy. Okay. So, delta G equal to delta G naught plus RT ln Q, and generally this N2 plus 3H2 tends to go to an equilibrium state. That is, if you are to plot the free energy of the reaction mixture as a function of the reaction, at some composition it will have the lowest free energy. Okay, some composition of ammonia, some composition of remaining nitrogen, some composition of remaining hydrogen, that will have the lowest free energy. Okay, so this is when at equilibrium, what is delta G? Delta G equal to 0. Second law says delta G should be 0 at equilibrium. So, delta G equal to 0, delta G, and at equilibrium Q becomes what? Q becomes K or Kp, pressure equilibrium constant or concentration dependent equilibrium constant. In this case, pressure is more suitable because terms are involving pressure. So, delta G naught equal to minus Kp. This is one of the fundamental relationship that relates equilibrium constant to the free energy change. Now, so far we have seen only free energy change with pressure. I am going to show you free energy change with temperature. That means you can correlate the equilibrium constant with temperature. How will the equilibrium constant vary with temperature? Why is it important? Yield. Finally, what are we interested in? Outcome. How much ammonia can I make at a given temperature? I am going to show you 3 examples. Okay, 3 simple examples of relevance today, where you will see that this is of extreme importance. Okay, 3 all practical things I am going to show you. So, let us go through it a little quickly now. So, this part I just derived on the blackboard. Okay, and this G by N, number of moles, is defined as a chemical potential. In order to compare something that happens in a reaction flask, invariably we normalize everything to 1 mole, because then it is easy to compare it per mole. So, G by N, chemical free energy by N, is defined as the chemical potential. So, this equation, which if I divide by N, what will it become? There is a nRT here, that gets cancelled out. It will become mu equal to RT ln P. Then it becomes very easy to compare whenever there is a mixture. Per mole is easy to compare. So, mu equal to mu naught. So, how does G vary with P? Very not directly important. From exam point of view, you might get a question like this. You will get a question like this: Gibbs free energy versus pressure. For a gas, Gibbs free energy increases with pressure, because dou G by dou P. What is dou G by dou P? dg equal to vdp minus sdt, dou g by dou p, yes, entropy, no. So, for a gas, in the gas phase with higher molar volume compared to liquid and solid phase is more sensitive to changes in Gibbs energy. In other words, Gibbs free energy with pressure will be always positive, with the positivity being much more for a gas compared to a liquid or a solid. This will be an exam question. You will always be asked Gibbs free energy change with pressure is always positive. First important thing is the slope of all these three lines is positive, positive, positive. G with P is always positive slope because volume increases. Okay, and for the gas, the V changes more compared to liquid compared to the solid. So, exam point of view, this is important. You can get this from dg equal to vdp minus sdt. Okay, from that you can get. Similarly, you can do that for how entropy change, because dou g by dou t at constant pressure is minus s. Okay, variation of free energy with temperature is minus s. But S, you know, is greater than 0 for all substances except at 0 degree Kelvin. S is always positive, S is never 0 except at 0 degree Kelvin. So, with temperature, free energy entropy relationship is minus. So, entropy should decrease with increasing temperature, and you see that indeed Gibbs free energy decreases with temperature because slope is minus s. For a gas, the variation is much higher, the slope is much higher for a gas, right? This slope, this is the slope, this is the slope, slope is much higher for a gas, this is the slope, less for a liquid, least, right? If a line is almost perpendicular, highest slope, infinite slope, anything less than a perpendicular, high slope, slope decreases as you come flat to x-axis where it becomes 0, infinity, 0, in between. Okay, so that is what these relationships tell you, how G varies with pressure and temperature. Now, last part is temperature dependence of G, so that how the equilibrium constant is affected by temperature. Okay, G is H minus Ts, you already know, and delta G equal to delta H minus T. Delta S is a simplest form of Gibbs-Helmholtz equation, simplest form. Okay, so you can write G minus H equal to minus Ts or Ts equal to H minus G. Suppose you divide by T, S equal to H minus G by T. So, keep this as a equation in your mind starting from 1. Second equation in mind is H minus G by T equal to S. And again, we always study closed systems, constant composition. Only work we consider is pressure volume work. We already know dou G by dou T at constant pressure is minus S. So, dou G by dou T at constant pressure is minus S equal to minus of, we just defined what S is, H minus G by T. So, dou G by dou T at constant P is nothing but G by T minus H by T, just from definition, nothing more than that. Okay. Then you do a small twist. Instead of this has nothing to do with the subject. Take a parameter G by T, another parameter G by T. Why? Because mathematically it is useful. And differentiate the G by T with respect to temperature. If you differentiate G by T with respect to temperature, you will get, it's a variable xy, x dy plus y dx. So, x dy, y dx. So, that will give you a term 1 by T into, within bracket, dou G by dou T at constant pressure minus G by T, which we defined in the last slide as equal to minus H by T. So, variation of G by T with P is minus H by T squared, and this is another form of the Gibbs-Helmholtz equation. Now, see where is G by T coming here? G by T, when the G by T comes here, what does this become? Nothing but equilibrium constant. This, if I take this, so this is nothing but Gibbs-Helmholtz equation is a form of variation of equilibrium constant with temperature. Simple form. Okay. So, the Gibbs-Helmholtz equation, I told you, when it comes to free energy, only 3 important things: minus delta G. Delta G should be negative for spontaneity, G varies with pressure, G varies with temperature, dG equal to VdP minus SdT is the equation of state. 4, finished, nothing else. Okay. So, this Gibbs-Helmholtz equation is fundamentally important. There is an alternate derivation, I am not going to go through it. Now, let us see whatever I stated to you in the first lecture. The first lecture, what did I tell you? This is an endothermic reaction. Remember the reaction of barium hydroxide with ammonium chloride. If you mix it up, it will become very cold. Okay. Now, when you plug in all the data from Atkins with respect to the heat of formation, the entropy of formation, you find that the delta H of this reaction you can actually calculate. You can calculate the delta H of this should be reaction, not formation. Reaction, you can calculate these numbers and you will find that the overall free energy change is minus 11.7 kilojoules. Therefore, an endothermic reaction is spontaneous because free energy change is still negative. Okay, it may be an endothermic reaction, but free energy change is negative. So, free energy change is what one should look for, not look for exothermic and endothermic reaction. So, this explains the first class, whatever we decided or discussed in the first class about exothermic reactions are spontaneous, endothermic reactions are spontaneous. Now, here is another thing, maybe let me write it down quickly. This should, I have to do it very fast because I do not have time. Okay. So, you have a reaction sign of delta G, let us say. Okay. Sign of delta G we are going to find out. So, delta H of reaction, delta S of reaction. What are the possibilities? Plus plus, plus minus, minus plus, minus minus. What is the fundamental equation you have to see? And that should be always negative, isn't it? Now you straight away see delta H is negative. Delta H is negative is exo, I will write. When I write exo, that means exothermic reaction. Okay. Suppose delta H is negative and delta S is positive. What happens? This is negative, this is positive. Temperature is always positive. So, the whole term will become totally negative. So, all exothermic reactions where the entropy of a reaction increases are always spontaneous under any condition, right? So, you can apply to 3 other specific conditions, okay? And let us see one practical consideration. Sir, I will finish in few minutes. Okay. Okay. So, you can, the previous reaction, you can actually identify the temperature at which this reaction will be in equilibrium by plugging in delta G equal to 0. You calculate, you find that at 5.3 degrees centigrade, if you mix these 2 salts, no heat will come out, no heat will be absorbed. So, that temperature is known as sealing temperature. First class we told you about sealing temperature, right? So, that is sealing temperature. Now, let us take a plastic example, practical example, polyethylene carry bag. Okay. The reaction is, what is the reaction? This I will keep, I will retain. Okay, I am just going to use the same thing that I have written on the left side. Use this. So, this is polyethylene is formed by the reaction of ethylene gas. I simply have to heat and apply pressure and also catalyst, okay, and that will give me this, and you have to always write the state of the system. Gas becomes a solid. When a gas becomes a solid, what happens to the entropy? Decreases. So, what is the case? Negative. And this contains a sigma bond and a pi bond, and this contains 1 sigma here, half sigma here, half sigma here, 2 sigma. So, 1 sigma plus 1 pi becoming 2 sigma. What will be the sign of delta H for that? It will be negative. So, delta H is negative because the pi bond becomes a more stable sigma bond. So, here is the condition, that is delta H is negative. So, delta H is negative and this is delta S is also negative. So, this I have to make it negative. So this term is negative, this term is a negative of a negative positive. So therefore at some temperature T, this will go in the reverse directions. So what does thermodynamics tell you about plastics? If you heat plastics to some temperature, it will spontaneously go back to the monomer in the reverse direction. Okay, and in fact plastics are, if you want to, I told you there is an energy cost and there is an economic cost. Economic cost we do not discuss in chemistry. Energy cost, it is foolish to heat a plastic and generate petrol. You can generate petrol, you can generate hydrocarbons by simply heating a plastic. It is simply not energy wise right decision or smart decision to convert a plastic to the monomers or other organic compounds. You can convert, it's a spontaneous, if provided you heat it to the right temperature. You heat it to the right temperature, and in fact in the case of polyethylene, if you take the data, if you plug in the data, thermodynamic data, it tells you at what temperature, around 1060. You have to heat it to 1060 degrees to convert polyethylene plastic back to ethylene gas, monomer gas, or other things also, you know. So this is a practical application of thermodynamics. So it is important that spontaneity has, you have to note again and again, I keep repeating time and again, spontaneity has nothing to do with the speed of the reaction. It simply has something to do with the direction, purpose. Okay, any quantity, delta G is 1 billion, 1 trillion, doesn't matter. As long as it is negative minus 0.1 and 1 trillion, 1 billion, doesn't make a difference. It is spontaneous in the direction. How do you push it? You push it using the Gibbs-Helmholtz equation. Whichever way you want to push it, study the Gibbs-Helmholtz equation, and then you can push it in the way you want, whichever direction you want to do. So remember this, spontaneity in chemical process always refers to the direction and nothing more. Rate depends on the mechanism. You have to study the mechanism or pathway and manipulate, understand it and manipulate, then only you can get the desired rate and also control products such as selectivity. Everything you have to understand the mechanism. Without understanding mechanism, you can't control selectivity of a product. Okay, with that, chemical potential, I am going to skip all these things. I am going to send this to you. Okay, only one last example of this, which is an important thing, is in extraction metallurgy, where this is extremely useful. Variation of G with T. Just now we discussed Gibbs-Helmholtz equation. Variation of G with T in extraction metallurgy, it is extremely important. Metal ores are extracted oftentimes by using carbon. Use a carbon along with metal ore. Normally metal ores are oxides or sulfides. This can also be an exam question. Why elements always occur in the oxide form or the sulfide form? So what you do is, when they occur in the oxide or sulfide form, you can react it with carbon solid, or you can react it with carbon monoxide gas and convert it to the pure metal. And the thermodynamics are given by these 4 equations. Okay, one is the formation of the oxide, other is formation of carbon dioxide, formation of carbon monoxide, and reaction of carbon monoxide with half oxygen gas to give carbon dioxide gas. And this was studied by Ellingham, a person by name Ellingham, and he came up with a diagram like this. An Ellingham diagram tells you, and you can easily lock into the temperature. This temperature, this metal ore will get reduced to the metal. This is available in the textbook, and in exam invariably you will get questions like this. Why aluminum oxide? What carbon, which form of carbon will be useful for reducing aluminum oxide to aluminum, nickel oxide to nickel, like that. But I will give you one example which I worked out for you just 1 hour before the class. I thought it will be very relevant because niobium is a paramagnetic metal. Okay, niobium is a paramagnetic metal, and in India 20% of our export money comes from automobile industry. So every 100 rupees India makes by way of export, 20 rupees comes from automobile industry. We are very big in terms of automobile industry. Automobile industries require magnets, and today over the last 6 months we are begging China. China is not happy with us, it is refusing to give us magnets. They ask us to go to their authorities and get license, and each and every company will have to go to the authority, write a letter. They are not willing to deal with government of India, they want to deal with individual companies. Now we are really struggling, and the other alternative source of magnet for us is Australia, Brazil and Canada. Okay, and here is niobium, which is a paramagnetic metal. Paramagnetic metal niobium, it occurs largely in Brazil and Canada, little bit in Australia, but mainly in Brazil and Canada. And niobium in the oxide form reacts with carbon to give you niobium metal. Okay. And here are the thermodynamic data. Heat of formation of niobium oxide, heat of formation of carbon in the graphitic form, niobium metal, carbon monoxide gas, and here is the data for the entropy. If you calculate the overall free energy of formation, it works out to be some number. Okay. You can calculate the delta H reaction, which is 1463.05 kilojoule per mole. You can calculate the delta S naught, which is temperature dependent. So, at what temperature you can reduce niobium? If you plug in the data, you will find that at 1298.7, roughly 1300 degrees centigrade, you can actually make the reaction go in the forward direction. At 298 Kelvin, this is delta G is positive, big positive. So, it does not happen. Therefore, you have to heat the carbon, and in fact, what you do is you heat it under vacuum at temperature above 2000 because of the kinetics. About 1300 you can do. You have to maintain vacuum because niobium metal is extremely sensitive to oxygen. So, in the real metallurgy, niobium metal is prepared by taking the oxide and mixing it with carbon, heating it above 2000 degrees centigrade under vacuum. You get niobium metal, and that niobium metal is not only important for automobiles, it is also important for mobile phones. Okay. So, like that, all rare earths are done in this manner, largely from oxide ore to the metal, which in turn plays extremely important role in night vision cameras, infrared cameras, mobile touch screen, everything requires rare earth metals, and non-linear optical application and so on. So, with that I am going to stop here. Okay, I will send you the notes, okay, where chemical equilibrium principle I have touched upon. You can derive Clausius equation from here. You can derive Clausius-Clapeyron equation, which are all practical experimental fact that the logarithm of vapor pressure varies directly with 1 more T is a practical consideration, it was experienced. Okay. How thermodynamic equations, equation of state helps you to derive the Clausius equation, Clausius-Clapeyron equation, and so on and so forth. I have given you several examples, and what I am going to do is, you remember thermodynamics is necessity. Without necessity, you can never ever get convenience. Kinetics is only convenience. You need a necessity, which is a fundamental factor, and convenience is whether the tea shop is nearby or it is 1 kilometer from here. But taking tea is necessary, isn't it? Right now we have to take tea. Luckily for us it is convenient. Kinetics is very low activation energy, we can just go out of the room and take tea. Okay. So, that is what you have to know the difference. Thermodynamics is always necessity, kinetics is convenience. Okay. With that I close, and all these things I will give in the notes, where I have given you how Nernst distribution law can be derived from thermodynamics. I have also given how the phase changes, physical phase changes, that can be done using the basic principles. Everything in a textbook comes from these principles. I already showed you. Everything can be derived if you have patience, you are willing to sit down, you can do all these things. Okay. With that, I really thank you. I also thank Professor Anbarasan for giving me summary. Also I have given what is the summary of all my lectures. So, this I will send it to one of you. Now, within 1 hour I will send you, okay, in the PDF form. With that, thanks a lot for giving me this, because I was feeling uncomfortable not being able to tell the basic minimum. I feel happy that I have been able to tell you the bare minimum in thermodynamics. Okay. Thank you.
SwayamPrabha, Digital India, Educated India.